Hello, this is Russell Hawley from the Tate Geological Museum, and today I'm going to be talking to you a little bit about the most abundant minerals in the crust of the Earth, and those are the silicates. It's a whole category of minerals that contain the element silicon. Mind you, that's silicon, not silicone. Silicone is an artificial rubber that they use to seal aquariums. It's something completely different. But silicon is an element, and it's a very important one because the most abundant mineral in the crust of the Earth is probably quartz, and the second most abundant is feldspar, and both of those are silicates. So we are living on a silicate world. Now, the building block, the basic building block of the silicate minerals is the silicate tetrahedron. Tetrahedron. How many sides does it have? Yep, it's got 4. 1, 2, 3, and then 4 on the bottom. And they are structured like this. You got to pretend that that black ball in the middle is a silicon atom, and that these white balls on the ends here are each oxygen atoms. So oxygen atoms, there's 4 places on a silicon atom that an oxygen atom can bond on there. And when they do, you end up with a little 4-sided pyramid like this, a tetrahedron. And some silicates aren't much more than a whole bunch of these guys all jumbled together. Notice that there are 4 times as many oxygen atoms as there are silicon atoms. So that ratio of oxygen to silicon is 4 to 1. That'll be important later. At any rate, there's other kinds of silicates that have a more complex structure than this, and they achieve that complex structure by sharing oxygen atoms. Let me show you what I mean. Here's another silicate tetrahedron, and here's another silicate tetrahedron. They each have the silicon atom in the middle and the oxygen atoms at the ends, but suppose they share one. We'll get rid of that oxygen atom there, and now they're going to share this guy right there. So now you've got a type of silicate called a sorosilicate. And in sorosilicates, the basic structure is 2 silicate tetrahedra joined point to point by sharing an oxygen atom. And notice that because they're sharing an oxygen atom, the ratio of oxygen to silicon has dropped. It used to be 4 to 1, or to put the same thing another way, 8 to 2, but now it's dropped to only 7 to 2. 7 oxygen atoms for every 2 silicon atoms. But you don't have to stop there. There are also cyclosilicates, from the Greek word for ring, cycle. So you can join 3 silicate tetrahedra together, point to point, in order to make a ring. And that's one kind of cyclosilicate. Or you can join 4 of them together, point to point, to make this kind of a ring. Or you can join 6 of them together, point to point, to make this kind of a ring. So those are 3 different kinds of cyclosilicates, rings made by joining the silicate tetrahedra together by sharing oxygen atoms. And notice that as these get more and more complicated, that ratio of oxygen to silicon keeps on dropping. Now, a very important sort of silicate, because there's a lot of it, are the Phillo Silicates. Phillo means leaf, because they're shaped like a bunch of flat leaves, one on top of the other. Each leaf is a sheet of silicate tetrahedra joined side to side to make a big, long, flat, 2-dimensional structure. There's a model of one of those right behind me. John Waterman and I built this over the course of a very tedious summer, but pretty impressive result, we felt. And here you can see all those silicate tetrahedra joined together in their sheets. And mica is a good example of a Phillo Silicate. Now you know why it is that mica breaks apart along one cleavage plane. It's because it is breaking in the spaces between those sheets of silicate tetrahedra, in between those leaves, so to speak. So those are the Phillo Silicates. Finally, there's one more kind of silicate, and those are the kind where all of the silicate tetrahedra are joined at every single point. So every tetrahedron in this structure is joined to 4 other tetrahedra by sharing an oxygen atom at each and every point. Those are called the tectosilicates. Tecto means framework, and because of this framework design, they're very, very strong. Quartz is an example of a tectosilicate. Because every corner is connected to another tetrahedron, they're sharing a lot of oxygen, and by the time you get to these guys, the ratio of oxygen to silicon has dropped to 2 to 1. And that's why the chemical formula for quartz is SiO2, 2 oxygen atoms for every 1 silicon atom.